Okay, so let us continue. Problem 4. Let t be the time needed to complete a job at a certain factory. By using the historical data, we know that the probability of capital T is less or equal than t when t is between 0 to 4 is given here. When t is greater or equal than 4 is equals to 1. Okay. And it asks us find the probability the job is completed in less 1 hour. So in other words, we're looking for the probability capital T is less or equal than 1. Noticing that this problem should be very straightforward, because when t is less or equal is between 0 and 4, so the probability is given here, right? So part A, that probability, which is just it's 1 over 16. Okay, there is really nothing you can scare of. Part B, find the probability that the job needs more than 2 hours. Okay, more than 2 hours. So basically, what we are looking for, right? So is this, and we can apply the complement, which is 1 minus p when t is less or equal than 2. And we know how to drive this. Just to substitute t equals 2 here, which gives us 1 minus 1 over 16 times 2 squared, which is 1 minus 1 over 4. It gives us 3 over 4. That's easy, right? Number 3 here. So it asks us to figure out what is the probability of t, right? So what you can think of is when t is between 1 and 3, what we can do is we can use the probability of t, the time less or equal than 3 hours, minus the probability of t is less or equal than 1 hour, right? So that would do the job. So it's 1 over 16 times 3 squared minus 1 over 16 times 1 squared. And it gives us is 9 over 16 minus 1 over 16, which gives us is 8 over 16. That is 1 over 2. So that completes the problem. Okay, still simple. All right, so let's see another one. Okay, so number 5, it said that a professor thinks students who lives on campus are more likely to get A's in the probability courses. Okay, you know, this problem is just a make-up problem. And to check this theory, the professor combines data from the past few years. Okay, so here's the data. 600 students have taken the course. Among those 600 students, 120 students got A. Okay. 200 students lived on the campus, and 80 students lived off campus and get A's. Okay. So does this data suggest that getting an A and living on campus are independent or dependent. Okay, or dependent. So, okay. So this problem, how do we do? Well, basically, what we're looking for, since it gives us two events, right? And then we want to check whether those two events are independent or not. Basically, what we're looking for is it's the probability of the intersection equal the product of the each probability. If that is true, then we claim that those are independent, right? Excuse me, let me drink some water. Otherwise, it's going to be dependent. Okay. So, what we can do is we can let's do this. We can see we can set the event A as a random student lives on campus. Okay. We can set the event B as that that student gets an A in this course. Okay, getting an A in this course. So based or students who get an A on this course. So basically what we are looking for is we're looking for if this is true or not, right? So if this equation good, then they are independent. Otherwise, it's going to be dependent, right? So what we can see? Well, the probability of a student who lives on campus, do you see that it's going to be 200 out of 600? It's going to be a third, right? And the probability of a student getting an A, do you see, is equals to 120 over 600. So it's equals to 1 over 5, right? 1 over 5. And noticing that, so those are the information we have used. But so this one we already used, this one we used, right? And this information we also used. But what about this information? So 80 students lived off campus, but still get an A. So what we can tell, this is what? This is the probability of A complement, right? Because it's we set the event A as a random student lives on campus. So if it's off campus, it's going to be A complement. While still the students get an A, so that's the event B. So do you see this is the probability of A complement intersect B, which equals 80 over 600, and that's 8 over 60, and of course you can do 2 over 15, right? 2 over 15. So that's what we can get. But how do we derive what is the probability of A intersect B. So the A intersect B can be viewed. So if you remember this, so this is A, this is a B. Okay. So we're looking for this, and then do agree that A intersect B can also be viewed as A minus A intersect A complement intersect B. So in other words, the probability of A intersect B can be viewed as the probability of B minus the probability of A complement intersect B. So which, as you can see that, the probability of B equals to 1/5, and the probability of A complement intersect B, which is 2/15. So to make a calculation, this is 3/15, so it turns out this is 1/15. And then the probability of A intersect B equals PA times PB, right? Because this is 1/15. This equals to 1/3 times 1/5. So hence, this is true. So we can drive that this event is independent, right? So those two are independent. So in other words, there's no relationship whether you live on campus or not to get an A or not. Okay. So let me address a little bit more about this part, because maybe some students still get confused. Let me get a new paper, maybe to draw this part and explain again. The thing is, you see, we're looking for A intersect B, right? So this is A, this is B, right? So to drive that this part, so A intersect B, we can also think about this. So first of all, A complement, which about this part, right? This is everything, this is A complement, okay? And then if you do, and so this is A complement, okay? And if you do n, okay, this is B, okay? If you do A complement intersect B, so this is A complement. If you do the intersection, so do you agree B is here? So if you do the intersection, do you agree it's here, right? So A complement intersect B, which is right here. So that's why A intersect B can be viewed as B minus A complement intersect B, right? Because you're looking for this pieces, so you use B doing the subtract. So that will do the job, okay? So that will serve this problem here, okay? That's number 5. Okay. Number 6. Okay, number 6. So it said that we have 5 cards. Okay, ideally from a shuffled deck. What is the probability that hand contains exactly one aces? Okay. And part B, it asks us, okay, what is the probability that the hand contains at least one aces here? So this is the a combination problem, right? So for part A, so the total number of the possible outcomes when we deal 5 cards from a shuffled deck is going to be 52 chooses 5, right? And if we want to have exactly one ace, because for a deck of cards you only have 4 aces, so you need to get one of the aces here, okay? And then after that, you choose 4 cards from the remaining 4 to 8 cards. So that will give you the probability of get exactly one ace here. Okay. Part B, we want to have at least one ace. Okay. So this type of the problem, you see, it get involved with this at least. What we want to do is, we still want to use the complement part. So in other words, what is the probability of there's no aces when we deal with 5 cards from a shuffled deck? Well, so that part is going to be 4 to 8 chooses 5, right? Out of 52 chooses 5. So that is a probability of there's no aces at all. And then, so the probability of at least one ace, do you agree it's just a complement of this? So just a 1 minus this one, and then that will do the work. Okay, so yeah, so that give you those 6 problems. So I hope you enjoy this. Thank you.